8.3 insertion sort. After we complete the insertion operation, we're almost there. Okay? Yeah, we just apply this insertion operation n-1 times, we get the whole array sorted. So let us just do analysis. Just like what we did before, we do the worst case, best case, average case analysis. All right. We count the number of compare and shift operation. Here we combine compare and shift operation. All right. So the diagram like this, the general diagram like this. First, let's look at the worst case efficiency. Worst case, every time when we do the insertion, we do the maximum number of compare and shift operation. Okay, So what do we have? Just like this, 1 plus 2 plus 3 to n-1. So that's this number. And if we write it in asymptotic notation, that's big theta of n squared. All right. The best case, every time we do the minimum number of compare and shift operation. So that's 1, but we need to do n-1 time. So that is n-1. Asymptotic notation, big theta of n. All right. Now, the last case, average case. So this is a little harder than the previous two cases. Answer is big theta of n squared. The question is, how do we see it? Right? How do you derive it? Can you do the calculation and get the answer of this? Here, let's work it out, all the details. All right. If you still remember, in our previous video, 8.2, we did average case cost analysis for insertion operation. We can use that. So we do not need to repeat that whole analysis process another time. Okay? So if you still remember, although we use approximate number, that's a good approximation number. 1/2 times k plus 1. All right. That's for each insertion step. When we insert a k into the current sorted array, we need to use this many operations on average. Now, let's look at all the insertion steps. So each insertion step, we use this average number. How about that? Okay, All right, so we do this. Summation. K from 1 to n-1. 1/2 k plus 1. Okay? Summation. I hope you know the properties of the summation operation. So we can write 1/2 k from 1 n-1 k. Okay? So that's the first part. Second part, 1, right? Summation 1. Okay? 2 parts. All right. The first part, 1/2, the constant, then the summation part formula. right? The formula is 1/2 times 1 plus n minus 1. So that's n times n minus 1. Plus this part, n minus 1 terms, each one 1, so you get n minus 1. Okay? This is a good estimate. Okay? Yeah. Yeah, so you can write, you want to simplify 1/4 n times n minus 1 plus n minus 1. Although you can simplify it if you want, but we can see the dominant term 1/4 n squared, right? 1/4 n squared. This is 1/2 n squared. So you can see the average case, 1/2 of the worst case, 1/4 n squared. So that's also in the big theta of n squared. So that is the analysis. Okay? Yeah. So I hope you can understand the calculation we did here. Okay? Especially the summation part. The basic summation part. All right. So that's the efficiency analysis part. Yeah. Next, conclusion. So we want to know the property of insertion sort. Insertion sort has some very special property. Yeah. So here, let me try to help you get to that special property. So what's that special property? Yeah. All right. So let's list that best case, big theta of n, worst case, big theta of n squared, average case, also big theta of n squared. All right. Now, here, I'd like you to compare the best case and the worst case. First, I want to ask you, under what situation the best case occurs? Under what situation can you imagine for what kind of data the best case occurs? Can you see that? All right, yeah. If you cannot see, yeah, let me tell you. So you try to figure out if that is the case. For the best case, the array, the given data array is already sorted. Is this the best case? The array already sorted, right? So every time when you do insertion, one comparison, sorted, one comparison, sorted, best case. So best case happens when the array already sorted. Definitely, here we mean ascending order, right? Yeah. Here we mean ascending order. Okay. If we do not say ascending, descending, we mean ascending. Okay. If it's descending order, we have to say in descending order. Yeah. If we do not say anything, when we say sorted, it must be ascending order. Okay. Yeah. All right. It looks natural, right? So when array already sorted, it's the best case. It looks natural, but it is natural only for insertion sort. Only for insertion sort. For most other sorting algorithms, they don't have this property. So that's something special for the insertion sort. For most of the other sorting algorithms, they don't have this property. For array already sorted, that corresponds to the best case. Okay, and yeah, I need to add another point. The best case and worst case difference is big. Big theta of n, big theta of n squared. The difference is big, right? The difference is big. Why I say this? Yeah, because for selection sort and bubble sort, the difference is 0, best case, worst case. The difference is 0, best case, worst case. Okay, although you can say it has this property, but the difference is 0. Okay, here insertion sort has this property. This situation corresponds to the best case, and the best case, worst case difference is big. These two together. That's the special property of insertion sort. For other sorting algorithm, you couldn't find this property. Okay? If the best case, worst case difference is big, then when your array is already sorted, it may not be the best case. It could be the worst case. Later you will see for some sorting algorithm, if you give this already sorted data, it corresponds to the worst case, not the best case. We will have one. We will have such sorting algorithm later. Yeah, so it's anti-intuition, but it is true. Okay, so that's why this insertion sort is quite special. Okay, so based on this observation, yeah, so this is a nice observation. Based on this observation, so now we can take advantage of this property. Okay, so we get an idea. So our conclusion: what is the best time to use insertion sort? The best time to use insertion sort. If the given array is almost sorted. If the given array already sorted, so then, yeah, you don't need to do anything, right? Yeah. But we know a given array is not completely sorted, but almost sorted. That could happen in some real world situation. This kind of data exists. Yeah. So under that situation, you need to think about the insertion sort. The insertion sort in that situation is the best choice. Yeah. Here, so far, as we know, no other sorting algorithm can do better than insertion sort for this special type of data. Yeah. If I draw a diagram, I can describe our data has this property. So the whole array almost sorted, but there is this red circle part. The red circle parts, they correspond to the out of order scattered locations. Yeah. Only in these, a few places, it's not sorted. We need to fix them. Other than that, already sorted. The most other parts already sorted. Okay? So this time, if we use the insertion sort, we can get efficiency close to big theta of n. Okay? So that's some really nice property. Otherwise, if the array is not sorted, then because the performance, no matter the worst case or average, even the average case, big theta of n squared, that's pretty slow. That's not a good performance. Yeah. So we have other better choices. In that situation, we won't. The general situation, we won't use the insertion sort, but only for the special situation, we use the insertion sort. Okay? So that is one big conclusion after we learned the insertion sort. All right. All right. Before we finish this part, there is another big, important, interesting result coming from insertion sort. So I also want to talk about that. Yeah. So that's also pretty interesting. Yeah. All right. Related to the insertion sort. Yeah. More specifically, why I want to talk about that, there is one big thing I want to discuss with you. So that is, remember in our first video, probably in our first video 8.1, I talk about one special thing. I'll ask you keep in your mind later sometime in the future. It could be very useful. I want to talk about that another time. So that is binary search based insertion. That kind of operation. Very interesting. Here, I want to show you why it is very useful. All right. Okay, all right. Okay, yeah. Sort. So we work on sorting problem. Sort. Sort what? Sort 3-element array. That's easy, right? Only 3 elements. What is the minimum number of comparisons? We need to get the minimum number of comparisons. For the worst case. Can you find it? What is that number? Minimum number of comparisons for the worst case, not the best case. Okay? Because if you use that number of comparisons to cover the worst case, then you just need that number to solve any case. So that's why we talk about worst case here. Okay? All right. This problem, so simple, only 3 elements. So everyone can solve it quickly, I believe. Right? So let's work it. Okay? All right. Suppose these 3 elements, I use x1, x2, x3. All right. Let's use insertion sort. How about that? Yeah, we just learned insertion sort, so it is natural we try to use insertion sort. Okay, all right. Sort first 2 elements, 1 comparison, right? 1 comparison, we can get it in order, so we just assume x less than x2. Okay, without loss of generality. Yeah. So here, in order to save our discussion sentences, okay, words, so we use without loss of. In math, we frequently use this term, generality, right? Without loss of generality. All right. So 1 comparison, we get this. All right. Now x3, we do insertion, right? So the worst case, you do 2 more comparisons, right? 2 more. Okay. 1 plus 2 equals 3. So your answer is 3. You need 3 comparisons to sort a 3-element array. For the worst case, for every case, right? If you can use 3 comparisons to solve sort 3-element array for the worst case, we can claim we can solve for any case with 3 comparisons. Okay, all right. So that's the first question. All right. Second question. All right. I increase the number from 3 to 4. How about that? When I increase the problem size, it becomes harder and harder, right? Harder and harder. So 4. How to solve 4-element array with minimum number of comparisons for the worst case. Now this time is harder. Okay? If you want to try, you may need to take a lot of time. Okay? You can try. Yeah, it's not, much harder than the 3-element problem. 4-element problem harder than 3-element, much harder. But it's doable. Yeah. For most of you, if you are willing to spend time, it's doable. Yeah. But here we just use the insertion sort to solve it. Okay, all right. This time, x1, x2, x3, x4. How about that? Okay, all right. So we have that. When we work on the problem, we use divide and conquer. Okay, can we solve the 3-element problem first without consider the last element? Let's solve the 3-element problem first. How about that? Conquer, yeah, we just solve it. So let us use the previous solution to solve the 3-element problem. So we need a 3 comparison, right? 3 comparison, we get the array sorted. Sorting result is like this. Without loss of generality, can we write this way? Yeah. Just the typical representation, right? Yeah. So we assume this typical representation. Although there are other cases, but essentially the same. Yeah. Similar situation. Yeah. All right. Yeah. Now to insert x4 into the sorted array, what is the best way we can do? Best way we can do. Okay? Binary search based insertion. That is the time to use the binary search insertion, based insertion. Compare x4 with x2. If it is smaller than x2, then we compare with x1. So you need 2 more comparisons. If it's greater than x2, you compare with x3. Also 2 more comparisons. You compare in the middle. Yeah. So you need 2 more comparisons. You sort the first 3 elements, you need 3, but then after that you need 2 more. 3 plus 2, your answer is 5 comparisons. You need 5 comparisons. You can sort 4-element array for the worst case. How about that? Can you do better than that? You cannot. Nobody can do better than this 5-element comparison for the worst case. Nobody can do it. This is optimal, the best people can do. Later we will prove it is optimal, okay? Later, after we learn some new knowledge, we will prove it. It is the best. Nobody can beat it. No matter who, nobody can beat this one. Yeah. All right. So you can see how important is this idea, how useful it is. All right. Let me give you another try, another example. Yeah. In order to show how important is this idea. Now, my last try, 5-element array. sort 5-element array. Can you do it? 5-element array. This is a really tough problem. Really tough problem. If you do not have the background of this module 4 part A, if you don't have this background, you can try 5-6 hours, you may not be able to solve it. Sort 5-element array using minimum number of comparisons for the worst case. Yeah. So you can ask anyone to do this. Yeah. Ask your friend. Yeah. Try to get a very smart friend to solve. Challenge your friends. Ask them to solve 5-element array with the minimum number of comparisons. And check if they can find the answer in 5 or 6 hours. 5 or 6 hours. The chance is very low. Yeah. Here we have the insertion sort background. We can solve it. Very, very simple way. All right, so let's do it. X1, X2, X3, X4, X5. Divide and conquer. So you know how powerful is this idea. Divide and conquer. All right. Divide. That's our subproblem. 4-element problem. Have we solved it already? We have solved it. 4-element problem, right? We need 5 comparisons. We get the first 4 elements sorted. Okay? After it is sorted, can we arrange in the ascending order? For simplicity, can we just use this x1 less than x2 less than x3 less than x4 for simplicity? All right. Oh, when you tell your friends for simplicity, you can tell them all the elements are different. Distinct elements. Different. Okay? Yeah. Because we don't want to discuss, if some of the elements are equal, but the, difficulty is the same. Okay? Just save some discussion words. Okay? Yeah. Make it simple. Yeah. That's why I write, strictly less than. Now, the 5th element, when we want to insert somewhere, we use the binary search-based insertion. Here, but which one you should, 4 elements, even number element, which one you should compare? Yeah. Compare one near the middle. Okay? Yeah. X2, X3, it doesn't matter. Yeah. So here, let's say we compare with X2 first. X2. X2, either less than or greater than, right? But you want to go to the greater than side. Insertion. Yeah, greater than, right. Greater than, looks like you need 2 more. Yeah. In that case, you need 3 more. Oh, 3 more, right. Then this may not be good. Yeah. So this way, yeah, this is not the best solution. Yeah. Because think about, yeah, so here it is a little different. Yeah, that's why it's challenging. Yeah. Because if you use 3 plus 5, 8, that's not the best solution. Yeah. Because the best solution is 2 more. So 7 comparisons. 7 comparisons, solve 5 elements. That's the best solution. Not 8. 8, not the best. Okay. All right. So let me just finish here. All right. part of 8.3. Yeah, that's it.